In this video, we're going to go over impulse, momentum, and the impulse-momentum theorem. So we've talked about how forces can cause a system or an object to accelerate, how a force can add energy to a system by acting on it over a distance. But what we're going to do in this video, or in this subject, is we're going to look specifically at collisions and how objects can transfer energy or momentum to each other through collisions. So first is just to think about it. Which is more difficult to stop? A tractor-trailer barreling down the highway at 35 meters per second, or a small two-seater sport car traveling the same speed? Hopefully you answered the truck, and all of that comes down to a quantity called momentum. Momentum is the quantity of motion of a moving object. And I know that doesn't sound that straightforward or simple, and in some ways momentum is so simple that it's difficult to define. So we sometimes call it inertia in motion because, remember, inertia is the mass of an object. So the more massive an object is, the more momentum it has and the more inertia it has. But a simple way of describing momentum is that it's a measure of how hard is it to stop something. So momentum depends not just on the mass, but also on the object's speed or velocity. Momentum is a vector, and that means that it does have a direction. And the direction of an object's momentum is always the same as the direction of the object's velocity. So momentum has a variable p, small p, not big P. So why is it a p since there's no momentum in p? Well, the reason is because when Isaac Newton first discussed it, he thought momentum was something so straightforward, so simple, so obvious that the p just stands for progress. So the equation for momentum is your momentum is equal to the mass of an object times its velocity. And unfortunately, unlike the units for newtons, where we took our kilogram times meters per second squared and made just a capital N, that has never been done for momentum. So momentum has awkward units. That's a kilogram times meter per second, or your mass units times your velocity units. Sometimes you will see it as a newton times a second, and that's usually when we calculate impulse, just because that's going to be force times time. So from here, what I want you to do is you can pause the video and practice applying this equation, momentum is mass times velocity, by working on practice problems 1 through 5 in your notes. For part 2, let's start with another question. Think about how you catch a water balloon to keep it from breaking. Pretend you're passing or throwing you're throwing a water balloon back and forth on an icy cold winter's day. What are you going to do to keep from getting yourself wet? Well, the answer to this question has to do with impulse. Impulse is the action of a net or external force during an interval of time. And an impulse causes a change in an object's momentum. Basically, an impulse is applying a force over time. So our variable for impulse is a capital J, and no, I don't really have an explanation for this one. And the equation is impulse is equal to force times time. So this is where our units of newtons times seconds come in. Now these two are equivalent. They're the same thing, because remember, a newton is a kilogram times meter per second squared. So if I multiply it times the second, this second cancels, and I end up with the same units as we had here. So how does this answer the question, though, about catching the water balloon? So when you bring an object to a stop, the impulse or change in momentum is the same regardless of how you stop it. So in order to make it so that it's not going to break, I want to have a smaller force. So if I want to have a smaller force, that means I have to increase the time in order to have the same impulse. So what do you do when you catch that water balloon? You go with it. You move your arms back as you try and catch it. You don't stick out your hand to make it come to a stop quickly, because if you do that, you're going to apply a large force over a small amount of time. So to catch the water balloon without breaking it, you want to increase the time by catching it more slowly, going back with it, and taking more time to bring it to a stop. Now, there's another thing we can do with impulse. With impulse and momentum, we can use the area under a graph. So when we're doing a constant force, we can use our equation. So this is only if we have a constant force. If the force is changing, you're going to be given a graph, and you're going to find the impulse by looking at the area under the graph. So this is the area with a constant force, and so it's just going to be force times time. And if you have a changing force, then same thing. If you have a force versus time graph, it's going to be the area underneath. Now, in this one, you have curves, so you would have to use calculus, but you could estimate it by doing a triangle. In most times, you would be given a graph that might be flat and then another angle so that you can make your shapes and add them together. But the impulse is the area under a force versus time graph. Make sure you know that. We are going to have an entire assignment just working on that. So go ahead and try practice problems 6 through 7, which are calculating impulse, and I believe there's one on the area under the graph. Okay, for part 3, we're going to start again with another question, and this is related to the question before. So why do you bend your knees when you jump off a table? Because hopefully you know that if you jump off a table or a chair, you don't want to keep your knees locked because that becomes very painful. So let's talk a little bit about impulse and momentum. When Newton first formulated the second law of motion, he did not actually write it in the form that we used when we studied dynamics. That was acceleration is equal to the sum of the forces divided by mass. He actually phrased it in terms of changing momentum. So a net force is equal to the change in momentum over time. And this becomes what's called the impulse momentum theorem. What this says is that the impulse applied to an object is equal to the object's change in momentum. So when we have a system that has constant mass, we often, well, hold on real quick. This basically is the form of the equation that you get on the AP formula chart. The only thing missing is it doesn't have net. So it's the change in momentum equals force times time. But in order to make the problem a little bit easier to work with, when we have a constant mass system, we can rewrite this equation as change in momentum is equal to mass times change in velocity. Because remember, momentum is mass times velocity. So if I have my final momentum minus my initial momentum, that would be my mass times my final velocity minus mass times my initial velocity, which would be mass times final minus initial. And this is equal to the change in velocity, so it's mass times change in velocity. So we can simplify or change the change in momentum to mass times the change in velocity. And then we can extend that equation that you have and have the impulse is equal to force times time, which is equal to the change in momentum, which is equal to mass times change in velocity. So as you try and solve impulse momentum theorem problems, you need to look at what information you have and what you're looking for in order to determine which portions of the equations you need to use. So for example, a problem might say that you have 10 units of your momentum changes by 10 units, and that takes 1 second. What's the net force? In which case you would have F delta T equals delta P. But you might have the final velocity and then comes to a stop, which means you have initial velocity. Your mass is 1 kilogram, and again it takes 1 second. What's the force? In which case you're going to use your F delta T is equal to M delta V. So find out what you have, what you're looking for, and pick the portions of the equation that you need to solve your problem. So going back to the jumper, again, this is similar to what we talked about last time. The jumper is going to change their momentum the same in both situations. Just before they hit the ground, they have a certain velocity downward. And it doesn't matter if they land with their knees locked or if they land with their knees bent. Just before they touch the ground, their velocity is the same. After they've come to a stop, their velocity is equal to 0. Mass doesn't change. So your change in momentum is the same no matter what. So what we're doing is we're messing with the second half of the equation. When you land with your knees straight, you're going to stop very, very quickly. And so that's going to be in a very small amount of time. And that means you're going to have a huge force. If you bend your knees, however, you increase your time, and that's going to give you a much smaller force, so it's going to hurt a lot less. So some other practical applications of the impulse momentum theorem. If you've ever seen those cute little hedgehogs, one of the reasons, or one of the things about their spines is they provide a cushion for the hedgehogs. So it's actually a little strange things that hedgehogs do is if they need to get out of a tree, it's actually not uncommon that they just roll themselves into a ball and fall, because their spines are going to cushion the blow and increase the time and decrease the force, and so they can easily survive a fall out of a tree, and it's just faster than crawling to the ground. Now, another thing we can look at if you're getting punched in the face. Well, what do you want to do? Do you want to just stand there and have the punch hit you, or do you want to back away from the punch a bit? Well, if you lean into the punch, you're going to be increasing the force by decreasing time. If you back away from it, you're going to increase time and decrease your force. So in order to have it hurt less, you don't want to lean into that punch, you want to back away from it. If you are driving a truck and you are going to come to a stop because your brakes aren't working, do you want to aim for the haystack or do you want to aim for the wall? Well, the wall is going to decrease the time it's going to take to come to a stop, but that means you're going to have a much larger force. The haystack is going to increase the time it takes to come to a stop and decrease the force. In both cases, the change in momentum is the same. The velocity in the beginning is the same. The velocity at the end is the same, both 0. So the change in momentum is the same. All that we're affecting is the time, and that will change your force. Or how about this one? If you are firing a cannonball, the cannon is going to fire with the same force regardless, so how can I increase the speed of the cannonball as it leaves the barrel? Well, if I have a longer barrel, that is going to allow that force to act for a larger time. So this time it's the same force, longer time. That means that my velocity is going to increase. So the same force, longer time will give me a larger velocity. So this is just using it a little bit different. So now I want you to try practice problems 8 through 13 on your notes page.